The graph in part C shows how the current varies with time. We can see the current starts with an initial high value, which we can call I0, and it is 1.68 milliamps. We have an interval of 0.2, and each of the 5 divisions correspond to a difference of 0.04. So the current decreases exponentially, as you expect from a charging capacitor. We then need to use the graph to show that the time constant is approximately consistent with the component values. Let's start with the component values. We need to remember that the time constant is given by R times C, where R is the resistance of the resistor in the circuit and C is the capacitance of the capacitor. So the resistance was 3 times 10 to the 3 ohms. It was given in the question that it's a 3 kilo ohm resistor, and we have a 100 microfarad capacitor, which we can write as 100 times 10 to the minus 6, and this will give us a time constant of 0.3 seconds. We then need to look at the graph and remind ourselves of what the time constant actually shows. The definition of the time constant is that it's the time taken for the current to be equal to the initial value over E, and this is 1 over E is about 37%, so this is 37% of the initial value. And we have already said that the initial value is 1.68 milliamps, so we can put that value in to get 0.62 milliamps. And we need to find the time taken for the current to go to 0.62 milliamps. So if we look at the graph and we go to 0.62 milliamps, which will be between the 2 lines there, and when we meet the graph we can go down and read the time from the graph there. So when the time is 0.25 there, the current will be 0.662, which is 37% of the initial current. And by definition, this time is the time constant T. So from the graph we have the time constant as 0.25 seconds. Therefore we can conclude that the two values, the one we get from the components, which is 2.3 seconds, and the value we get from the graph, which to one significant figure we can also write as 0.3 seconds, these values are consistent.